Okay, let's continue our discussion on response to support motion. So this a response to support motion is actually the basis of earthquake engineering. Since all ground shaking may be considered as support motion, so most of the problems in earthquake are fundamentally uh, or basically related to this type of excitation. Okay, so the support displacement that is mentioned here is not the initial displacement. So these are actually a continuous motion of the support that will induce the body, the mass, to vibrate. Okay, so if we consider here a mass spring system without including yet the damping uh, consideration, so we can actually create a free body diagram of the motion considering y coordinate and x coordinate as your absolute coordinates. Okay, so if we are now going to look into the relationship of the elements of vibration, which is the spring and the mass. The mass is actually related to your y coordinate, while your spring is related to both x and y, such that your forces here in this free body diagram is given by the spring force ky, okay, minus x, and my double prime. Okay, so if we add the two, there are no forces involved, considering a free uh, vibration. We now have a simple differential equation of motion in the form my double prime plus k quantity y minus x equals 0, and this can be transformed into a simple differential equation of motion, which is a now a force uh, undamped vibration. Um, but basically, the variable of consideration are not uh, just one variable of coordinate, but we are using two coordinate system in x and y. Both are actually absolute. Okay, for the support acceleration, most earthquake engineering problems are uh, using the acceleration variable rather than the displacement variable. Okay, so when we talk of ground motion or ground shaking, which is actually the basis of earthquake motion, we are usually using or commonly using the support acceleration in terms of the support motion. So if we just change a variable, this the displacement variable into the acceleration variable, all we need to do is to put an x double prime here and then xo double prime to represent acceleration parameters. Okay, and if we add damping, the spring and the dash pot here will actually be related to the uh, to both, okay, y and x coordinate in terms of a relative coordinate. So y is relative to x and y prime is also relative to x prime, but your mass is still dependent only on the y or the y coordinate variable as shown here in this model or system. Okay, so you can see that y is only attached, the mass is only attached to the y coordinate, it's not attached to this frame of reference, which is the x coordinate, moving uh, back and forth to represent motion. Okay, so if we now continue uh, deriving a relation and converting the absolute parameters into a relative parameter u, we now see that u is representing a relative motion of y minus x, and if we solve for y, we can say that uh, y is equal to u plus x. So it's better to get a relative variable for simpler DEM equation, with of course the absolute x variable still remains, because x is actually a given. Okay, this coordinate x is a given parameter, which is simply the support motion parameter or the earthquake parameter that is uh, normally known to us. So if we substitute this relative variable in terms of or sorry, the absolute, yes, relative variable u in terms of y, or y in terms of u, so we can now come up with this absolute x and y variable transformation to a relative u variable. Okay, so we ignore the absolute variable x simply because, again, as I have said, this is a known variable. So this is a more common and more appropriate, such that we again converted the DEM, the free vibration, into a forced vibration simply by taking note that the forces is simply the mass of the system multiplied by the acceleration of the support. Okay, so for a single degree of freedom system, the model can be seen or represent this um, uh, rad mass model. Okay, so this is a stick model, they call it a stick model or a rad mass model. Okay, so the stick models now represent vibration laterally, which is much more closer to a vertical structure, which is a building, okay, a shear building model. So if the motion on the ground is defined in terms of the support acceleration x double prime, then we can simply substitute this value here to represent the force, the force in the mass spring damper system. Okay, and the force is simply an equivalent static force P derived from the uh, inertia force m x double dot or double prime, or simply the mass times the acceleration. So we can now move a little bit higher into the level of transmissibility problems, or what you call the degree of relative isolation, which tells us how much of the support motion is transmitted to the mass. Okay, so this transmissibility problem is not only applicable to buildings, but also to other structures like foundation, uh, diaphragm walls, slabs, beams, wherein the acceleration and motion is induced by, maybe by not only by movement of the base, but also the motion of certain equipment, machinery, motors, etc. Okay, so considering now a harmonic excitation of x, a function of sine omega t multiplied by an initial displacement there, we now derive a differential equation of motion response as we have done um, earlier, the same procedure. So we have the mass multiplied by y double prime, then c, this is multiplied by your absolute velocity minus. Okay, so this is now your um, uh, harmonic excitation in terms of velocity. Okay, so this is I think there is an error here in the, this must be x. Okay, xo prime. So you will notice that the derivative of x is x prime is equal to xo. The derivative of sine is cosine omega t, and then if we take a derivative of the inner expression here, so we simply multiply it still by omega, such that this becomes xo omega cosine omega t. So there's no prime here. Okay, so that's correct. Okay, so that's xo omega. Okay, so no error there. So this is now x prime. Okay, that's the x prime there. So okay, plus ky minus xo sine omega t equals 0. And of course, we have to separate the variables of concern from y to x here. Okay, so all those who have x remains on the right side, which represents the forcing function, and this represents the mass spring and the damper variables. Okay, so the equation can also be written in the following form by simply uh, simplifying this. Okay, so this is a cosine sine function which can be represented by a single trigonometric sine plus sine of okay, omega t plus a phase angle. Okay, so remember that if you define a phase angle, the sine and cosine graph can actually be converted simply by the cosine wave. Okay, by simply introducing a phase angle that will trans or shift, no, the axis, the origin. Okay, the origin going to the left or going to the right, depending upon the sign of your phase angle here. So this is a simpler equation, and if we take a look into a detailed derivation of this. From this going to this, we now define another variable p. Okay, so p is equal to xo, the square root of k squared. Another variable introduced is k. So plus quantity c omega squared is equal to a much simpler xok. K lambda is all again defined in terms of k or vice versa, and also an r is defined in terms of the ratio of your what's this, the frequency of the vibration. Okay, frequency of vibration. So if this is an earthquake problem, this is the frequency of the ground shaking, no? So, and this is the natural frequency, so don't be confused with these two here. The natural frequency is the inherent in the system, while the frequency of motion or frequency of vibration or motion is a given frequency of shaking. Okay, so there is in your reference, there is a more detailed explanation on how these parameters were derived one from the other. Okay, so the steady state solution therefore of the DEM is can be um, finally obtained by simply looking into the format of your force damp vibration that we have derived earlier, no? Okay, so this is the format very similar to what we derived. So this P over K now is separated because this defines your uh, static. Okay, so this is the static part. Okay, so this is simply the static um, part of your deflection or simply response. Okay, and the rest is actually a considered as a magnification factor. Okay, so this is simply the dynamic magnification factor in terms of this. And of course, theta is again introduced here, which is simply 2 lambda r over 1 minus r squared. Okay, so substituting the value, substitute p in this equation in terms of we know that p is equal to k xo. Okay, so p over k, so xo is simply p over k. So if we substitute xo here as your static response and divide it there, so this is your ratio, and again the ratio is actually the relative transmission of the support motion to the oscillator, which is important in vibration transmissibility analysis. Okay, so this is now your transmissibility TR. Okay, so if you want a factor to indicate uh, your percentage or your degree of transmissibility, then you have TR as your factor. Okay, so for transmissibility issues, you term this as your transmissibility. For deflection computation or response computation, you call this as your magnification factor. And of course, if transmissibility is big, your magnification is big. If your transmissibility is low, your magnification is low, okay, and vice versa. So in terms of degree of isolation, it's the reverse, no? The transmissibility is actually the reciprocal of the degree of isolation. So if I term this as letter I, okay, so TR is the reciprocal of isolation. If the transmissibility is high, the isolation is low. If the transmissibility is low, isolation is high. Okay, in terms of relative motion, we go back to this original difference relative y minus xt situation. We can convert the yt with ut here by simply taking note that yt minus xt, sorry, yt minus xt is simply the relative motion. Okay, so this is now in a simpler format. Okay, so the denominator remains unchanged, but the numerator was a little bit more simpler. Okay, so here we are looking into the absolute transmissibility. So this is a relative transmissibility. So note that for maximum values, if we want to get a maximum value, this parenthesis must the value of this in the parenthesis using sign must have angles that will represent values equal to 1. Okay, so the situation is that your omega cannot be changed, but theta, the phase angle here, can be changed into such that this part here becomes a maximum. So if we place this equal to 1, then your simple equation for relative, for absolute will be, this will be 1, and for relative this will be 1. So these are the two equations of transmissibility that will represent both absolute and relative coordinates. Okay, so that's it for the support motion principle and the transmissibility concepts.